We're starting a new unit in this module, and we'll talk about density of measures. It's good to keep in mind that measures having density with respect to another measure is the exception, not the rule, but nevertheless, we'll see that exception coming up many times. So to start, what we have is we're going to define a new measure nu from a measure mu. So we have a measure space where mu is the measure in that measure space, and we have a non-negative function there. Okay, it's an extended function. It can take value infinite at some points. It's okay. And this f will be later on what we call density. We'll see. It's how do we assign a different weight to a set A if we already have a predefined way to assign weights to sets. So this is a different way of assigning weights, and it is the following. Each set A will restrict our measure to that set A, which means multiply whatever function by this indicator here, and integrate the function f on that set A. For instance, if we take f, the function constant equal to 1, okay, the function that takes value 1 at every point, if this is f in this example, then we have nu will be simply the same as mu. Because here there's nothing to integrate, we're integrating 1 here, and then this becomes the measures being the same. And if f is not constant equal to 1, it means nu is assigning different weights, and f is tuning or adjusting the weights of the sets that nu will give them comparatively to the weights that mu was giving there. So now for the proposition, excuse these moments of silence. So to prove the proposition, we have to prove that this object we're defining here, we're defining this object through this formula, plugging a here and computing the integral. We have to prove that this indeed defines a measure, and it is a very nice exercise for you to do. It allows you to connect the definition of measure with properties of the integral, of the Lebesgue integral of non-negative functions, especially it being a sigma additive. So it is a very nice exercise for you to prove this proposition. And just to say a few more words about the idea of what it means to define a new measure by integrating a function on sets, we can think this function is amplifying the measure mu or attenuating the measure nu at different places. So if f only takes finitely many values, so we look here at the space omega, there is some place in omega where f takes value 1, another place where f takes values 2.5, and another place where f takes value 0, let's say, then this new measure, it will assign measure 0 to any set here. To any set here, it will assign the same measure as mu. To any set here, it will assign 2.5 times as much measure as a mu. And if you have a set that overlaps all these regions, well, then you will have to decompose this set into bits. And well, one bit will be discarded, the other bit will have the same weight, and the other bit will have the slightly or try 2.5 more times measure. And this is what f is doing. So this is a density, means this is an amplifying factor that you apply to the measure mu. Well, but in interesting cases, f does not need to take only 3 values, as in this example here. F can take a continuum of values, which means the way it is amplifying the base measure, let's call this the base measure, mu, can vary continuously. So here's an example that will help you connect with your previous notion of density, if you have heard that word before in other contexts. So consider this measure space, the real line with Borel sets and the Lebesgue measure. And now I'm going to introduce a function. I'm now calling it g instead of f. I'm introducing a function, and this is the function. It is 0 if x is negative, and if x is not negative, it will be some lambda times e to the exponential of minus lambda x for some positive number lambda, which is fixed. So lambda is fixed, and this formula is for every x. Okay. Then we can define a new measure on the real line. I'm going to denote this measure by p lambda. I'm using the letter p instead of a Greek letter nu or mu. You can already guess why I'm using p instead of mu or nu. I'm going to define a new measure by evaluating the measure at sets in this way. I just put the set here. I integrate this function g over that set, and which is the same, we know. This is by definition the same as integrating the whole real line, function g multiplied by indicator of the set, and integrating it against the Lebesgue measure. So by the previous proposition, this one we just saw, this defines a measure on the real line. Well, and in fact, it is a probability measure. We can see it is a probability measure. How? Well, by integrating. We integrate this function here. Well, it is 0 on the negatives, so we can integrate it only on this interval here. And we know what happens when we know what happens when we integrate functions on the whole semi-line, half-line, infinite line. Well, this is a non-negative function, so we can use monotone convergence theorem. We can integrate from 0 to n and then take a limit. We integrate from 0 to n, and then we take a limit in n, and we know how to compute this. And we compute this integral, and we get 1. That's not a coincidence, of course. The example was chosen deliberately so that this measure of the entire real line would be 1. That's why it is a probability measure. And as we know, this expression here, this is the density of a random variable which has exponential distribution. But for now, let's just focus on the fact that we started from some measure. Well, the Lebesgue measure, this is the main measure we work with. We started with some Lebesgue measure on the real line, and we use it to construct a probability measure on the real line using a density. So we specified a density, and this gave us a new measure.